Thermodynamics is a branch of physics concerned with heat and temperature and their relation to energy and work. It defines macroscopic variables, such as internal energy, entropy, and pressure, that partly describe a body of matter or radiation. It states that the behavior of those variables is subject to general constraints that are common to all materials, beyond the peculiar properties of particular materials. These general constraints are expressed in the four laws of thermodynamics. Thermodynamics describes the bulk behavior of the body, not the microscopic behaviors of the very large numbers of its microscopic constituents, such as molecules. The basic results of thermodynamics rely on the existence of idealized states of thermodynamic equilibrium. Its laws are explained by statistical mechanics, in terms of the microscopic constituents. Thermodynamics applies to a wide variety of topics in science and engineering, especially physical chemistry, chemical engineering and mechanical engineering. Historically, the distinction between heat and temperature was studied in the 1750s by Joseph Black. Characteristically, thermodynamic thinking began in the work of Carnot, who believed that the efficiency of heat engines was the key that could help France win the Napoleonic Wars. The Irish-born British physicist Lord Kelvin was the first to formulate a concise definition of thermodynamics in 1854. Thermodynamics is the subject of the relation of heat to forces acting between contiguous parts of bodies, and the relation of heat to electrical agency. Initially, thermodynamics, as applied to heat engines, was concerned with the thermal properties of their working materials, such as steam. In an effort to increase the efficiency and power output of engines, thermodynamics was later expanded to the study of energy transfers in chemical processes, such as the investigation, published in 1840, of the heats of chemical reactions by Germain Hess, which was not originally explicitly concerned with the relation between energy exchanges by heat and work. From this evolved the study of chemical thermodynamics and the role of entropy in chemical reactions. Introduction. Historically, thermodynamics arose from the study of two distinct kinds of transfer of energy, as heat and as work, and the relation of those to the system's macroscopic variables of volume, pressure and temperature. As it developed, thermodynamics began also to study transfers of matter. The plain term, thermodynamics, refers to a macroscopic description of bodies and processes. Reference to atomic constitution is foreign to classical thermodynamics. Usually the plain term, thermodynamics, refers by default to equilibrium as opposed to non-equilibrium thermodynamics. The qualified term, statistical thermodynamics, refers to descriptions of bodies and processes in terms of the atomic or other microscopic constitution of matter. Using statistical and probabilistic reasoning, thermodynamic equilibrium is one of the most important concepts for thermodynamics. The temperature of a thermodynamic system is well defined, and is perhaps the most characteristic quantity of thermodynamics. As the systems and processes of interest are taken further from thermodynamic equilibrium, their exact thermodynamical study becomes more difficult. Relatively simple approximate calculations, however, using the variables of equilibrium thermodynamics, are of much practical value. Many important practical engineering cases, as in heat engines or refrigerators, can be approximated as systems consisting of many subsystems at different temperatures and pressures. If a physical process is too fast, the equilibrium thermodynamic variables, for example temperature, may not be well enough defined to provide a useful approximation. Central to thermodynamic analysis are the definitions of the system, which is of interest, and of its surroundings. The surroundings of a thermodynamic system consist of physical devices and of other thermodynamic systems that can interact with it. An example of a thermodynamic surrounding is a heat bath, which is held at a prescribed temperature, regardless of how much heat might be drawn from it. There are four fundamental kinds of physical entities in thermodynamics: states of a system, and the states of its surrounding systems, walls of a system, thermodynamic processes of a system, and thermodynamic operations. This allows two fundamental approaches to thermodynamic reasoning, that in terms of states of a system, and that in terms of cyclic processes of a system. A thermodynamic system can be defined in terms of its states. In this way, a thermodynamic system is a macroscopic physical object, explicitly specified in terms of macroscopic physical and chemical variables that describe its macroscopic properties. The macroscopic state variables of thermodynamics have been recognized in the course of empirical work in physics and chemistry, always associated with the material that constitutes a system, its working substance, are the walls that delimit the system, and connect it with its surroundings. The state variables chosen for the system should be appropriate for the natures of the walls and surroundings. A thermodynamic operation is an artificial physical manipulation that changes the definition of a system or its surroundings. Usually it is a change of the permeability of a wall of the system, that allows energy or matter to be exchanged with the environment. For example, the partition between two thermodynamic systems can be removed so as to produce a single system. A thermodynamic operation that increases the range of possible transfers usually leads to a thermodynamic process of transfer of mass or energy that changes the state of the system, and the transfer occurs in natural accord with the laws of thermodynamics. But if the operation simply reduces the possible range of transfers, in general it does not initiate a process. The states of the system's surrounding systems are assumed to be unchanging in time except when they are changed by a thermodynamic operation, whereupon a thermodynamic process can be initiated. A thermodynamic system can also be defined in terms of the cyclic processes that it can undergo. A cyclic process is a cyclic sequence of thermodynamic operations and processes that can be repeated indefinitely, often without changing the final state of the system. For thermodynamics and statistical thermodynamics to apply to a physical system, it is necessary that its internal atomic mechanisms fall into one of two classes. Those so rapid that, in the time frame of the process of interest, the atomic states rapidly bring system to its own state of internal thermodynamic equilibrium, and those so slow that, in the time frame of the process of interest, they leave the system unchanged. The rapid atomic mechanisms account for the internal energy of the system. They mediate the macroscopic changes that are of interest for thermodynamics and statistical thermodynamics, because they quickly bring the system near enough to thermodynamic equilibrium. When intermediate rates are present, thermodynamics and statistical mechanics cannot be applied. Such intermediate rate atomic processes do not bring the system near enough to thermodynamic equilibrium in the time frame of the macroscopic process of interest. This separation of time scales of atomic processes is a theme that recurs throughout the subject. For example, classical thermodynamics is characterized by its study of materials that have equations of state or characteristic equations. They express equilibrium relations between macroscopic mechanical variables and temperature and internal energy. They express the constitutive peculiarities of the material of the system. A classical material can usually be described by a function that makes pressure dependent on volume and temperature, the resulting pressure being established much more rapidly than any imposed change of volume or temperature. The present article takes a gradual approach to the subject, starting with a focus on cyclic processes and thermodynamic equilibrium, and then gradually beginning to further consider non-equilibrium systems. Thermodynamic facts can often be explained by viewing macroscopic objects as assemblies of very many microscopic or atomic objects that obey Hamiltonian dynamics. The microscopic or atomic objects exist in species, the objects of each species being all alike. Because of this likeness, Statistical methods can be used to account for the macroscopic properties of the thermodynamic system in terms of the properties of the microscopic species. Such explanation is called statistical thermodynamics. Also often it is referred to by the term statistical mechanics, though this term can have a wider meaning, referring to microscopic objects, such as economic quantities, that do not obey Hamiltonian dynamics. History. The history of thermodynamics as a scientific discipline generally begins with Otto von Guericke, who, in 1650, built and designed the world's first vacuum pump and demonstrated a vacuum using his Magdeburg hemispheres. Guericke was driven to make a vacuum in order to disprove Aristotle's long-held supposition that nature abhors a vacuum. Shortly after Guericke, the physicist and chemist Robert Boyle had learned of Guericke's designs and, in 1656, in coordination with the scientist Robert Hooke, built an air pump. Using this pump, Boyle and Hooke noticed a correlation between pressure, temperature, and volume. In time, they formulated Boyle's law, which states that for a gas at constant temperature, its pressure and volume are inversely proportional. In 1679, based on these concepts, an associate of Boyle's named Dennis Papin built a steam digester, which was a closed vessel with a tightly fitting lid that confined steam until a high pressure was generated. Later versions of this design implemented a steam release valve that kept the machine from exploding. By watching the valve rhythmically move up and down, Papin conceived of the idea of a piston and a cylinder engine. He did not, however, follow through with his design. Nevertheless, in 1697, based on Papin's designs, the engineer Thomas Savery built the first engine, followed by Thomas Newcomen in 1712. Although these early engines were crude and inefficient, they attracted the attention of the leading scientists of the time. The concepts of heat capacity and latent heat, which were necessary for development of thermodynamics, were developed by Professor Joseph Black at the University of Glasgow, where James Watt worked as an instrument maker. Watt consulted with Black on tests of his steam engine, but it was Watt who conceived the idea of the external condenser, greatly raising the steam engine's efficiency. All the previous work led Sadi Carnot, the father of thermodynamics, to publish Reflections on the Motive Power of Fire, a discourse on heat, power, energy, and engine efficiency. The paper outlined the basic energetic relations between the Carnot engine, the Carnot cycle, and motive power. It marks the start of thermodynamics as a modern science. The first thermodynamic textbook was written in 1859 by William Rankine. Originally trained as a physicist and a professor of civil and mechanical engineering at the University of Glasgow, the first and second laws of thermodynamics emerged simultaneously in the 1850s, primarily out of the works of William Rankine, Rudolf Clausius, and William Thomson. The foundations of statistical thermodynamics were set out by physicists such as James Clerk Maxwell, Ludwig Boltzmann, Max Planck, Rudolf Clausius and J. Willard Gibbs. From 1873 to 76, the American mathematical physicist Josiah Willard Gibbs published a series of 3 papers, the most famous being On the Equilibrium of Heterogeneous Substances. Gibbs showed how thermodynamic processes, including chemical reactions, could be graphically analyzed. By studying the energy, entropy, volume, chemical potential, temperature and pressure of the thermodynamic system, one can determine whether a process would occur spontaneously. Chemical thermodynamics was further developed by Pierre Duhem, Gilbert N. Lewis, Merle Randall, and E. A. Guggenheim, who applied the mathematical methods of Gibbs' etymology. The etymology of thermodynamics has an intricate history. It was first spelled in a hyphenated form as an adjective in 1849 and from 1854 to 1859 as the hyphenated noun thermodynamics to represent the science of heat and motive power, and thereafter as thermodynamics. The components of the words thermodynamic are derived from the Greek words theta epsilon rho mu eta therm, meaning heat, and delta epsilon mu alpha mu iota sigma dynamis, meaning power. The term thermodynamic was first used in January 1849 by William Thomson, later Lord Kelvin, in the phrase a perfect thermodynamic engine to describe Sadi Carnot's heat engine. In April 1849, Thomson added an appendix to his paper and used the term thermodynamic in the phrase the object of a thermodynamic engine. Pierre Perrault claims that the term thermodynamics was coined by James Joule in 1858 to designate the science of relations between heat and power. Joule, however, never used that term, but did use the term perfect thermodynamic engine in reference to Thomson's 1849 phraseology, and Thomson's note on Joule's 1851 paper on the air engine. In 1854, thermodynamics, as a functional term to denote the general study of the action of heat, was first used by William Thomson in his paper on the dynamical theory of heat. In 1859, the closed compound form thermodynamics was first used by William Rankine in a manual of the steam engine in a chapter on the principles of thermodynamics.